All right, let's finish up 3.3. This is 3.3 part 2. All right, I know there's a lot going on this page, but we're just looking at our blood types again. Okay, so the first one is find the probability that a donor selected at random has type B or type AB. So this is let's go up to the top left-hand corner here. So I want type B or type AB. So these are mutually exclusive. There's nothing in common because they're in different columns and because you can't be both. You can't be B and AB. You're one or the other. These are mutually exclusive. So I can just take the probability of B, which would be the 45 over 409. That's what I have right here. And then I can take the probability of AB, which is 16 over 409. That's right here. I'm gonna let my calculator add them together, turn it into a decimal. And so I get that the probability that a donor selected at random has type B or type AB is 0.149, not very high. Okay, type 2 wants the probability that a donor selected at random does not have type O or has type A. Okay, does not have type O or has type A. So there's a couple different ways to do this. I did it the way the book did here in red, but let's not do that. Let's just add up what we need. So you're going to take the 164 plus 45 plus 16 and divide all of that by 409. So I have 164 plus 45 plus 16. These are all either A or not type O, and we're going to put that over 409. And that gives us 0.550 over here, which is the same as using that formula. Okay, then number 3 is down here. This is an issue for this one because we have to be careful. We're looking at type O. That would be this column right here. We're also looking at RH positive, which would be this row. So notice there's an intersection, right? The 156 in the middle here is counted twice. So I have to be careful. So what I'm going to do is take the, where am I? I'm going to take the probability of type O. So that would be 184 over 409. That's right here. I'm going to take the probability of RH positive. So that's the 344 right here that I put in my formula here. And then because the 156 is counted twice, it's counted in the 184. It's also counted in the 344. So I need to subtract it out because it's double counted. I need to subtract one of those counts out. And that's right here, subtracting 156, put it all over 409. And oh my goodness, after all that, I get 0.909. That's very high. So the probability that a donor selected at random has type O blood or RH positive is 0.909. So this is just a reminder of what we've done so far. We looked at classical probability where we took the number of outcomes in event E over the total number of outcomes in the sample space. We had empirical probability. That's when we had surveys or observations, and we took the frequency of event E over the total frequency. This range is very important. Probabilities have to be between 0 and 1, inclusive. So they can be 0, they can be 1, or anything in between, but they can't be less than 0, they can't be greater than 1. Then we did complements, right? So the probability of E prime or E naught or the complement of E is equal to 1 minus the probability of the event E. Then we looked at multiplication rule. If you see in probability, if you see the word and, you're going to multiply. It just matters if you have a dependent event or an independent event, then you have to use the given that. And then in this section, we used addition rule. So you see the word or, that means you're going to add. You just have to be careful if you have intersection. Then you've got to subtract because you double count. Okay, let's take a look at some problems that look sort of like the homework. So the percent of college students' marijuana use for a sample of 97,448 students is shown in the accompanying pie chart. The probability of each event is, find the probability of each event. Okay, so our pie chart has marijuana use in the last 30 days. Blue is that they never used it. Red is they used it, but not in the last 30 days. Green is they used 1 to 9 days. Yellow, they used it on 10 to 29 days. And finally, purple is they used all 30 days. Okay, and then they gave us all of the percents next to it. So the first one is find the probability of randomly selecting a student who has never used marijuana. Well, they gave us that one, right? That's right here, 52.9%. And we're going to put that in right here. Then they say randomly select a student who has used marijuana. So you have two choices. You can either add up all the other ones, right? Because those are people who've used it. The question in B doesn't say anything about how many days or when. It just says people who used it. So you can either add up the other four pieces of the pie, or you can use the complement, right, and take 100% minus the 52.9% that never used. So either way, you're going to get 47.1% here. Okay, then they say randomly select a student who used marijuana between 1 and 29 of the last 30 days. Okay, well, 1 and 29 would mean that I would need the 14% here and the 6% here, right? Because I would have 1 through 9 and 10 through 29. So that would give me 20%. And then finally, randomly selecting a student who used marijuana on at least one of the last 30 days. So that would mean I'd also have to include this 2.1 because they want one of the last 30 days. So the first two pie slices aren't going to work, but I could add the last three, and that gives me 22.1%. So not a lot of calculating, more just reading the graph. All right, this is an interesting problem. You got to be careful with your graph. So we have 989 adults were surveyed, and we have the responses about the story of Britain's vote to leave the European Union. So they say, how important is the Brexit story to you personally? Now you have to be careful because this is a Pareto chart. So it's not A, B, C, D, E, F. It's not in order of letters. It's in order of how much frequency you have. So C is actually the first pie chart here, or excuse me, bar, the first bar on the bar chart, not a pie chart. C has 312 responses. And if you come down here to C, C is actually answering somewhat important. So A is extremely important, but that is way over here, that bar. B is very important, that bar is here. So you just have to watch carefully on this. All right, so the first question is randomly select an adult who thinks the story is somewhat important. Well, somewhat important means that we want C. I went ahead and wrote my frequencies next to the table. That just helped me find them. But C would be 312 up here. So I'm going to put 312 over the 989 responses. And that tells me the probability of randomly selecting an adult who thinks the story is somewhat important is going to be 0.315. Then they say randomly selecting an adult who thinks the story is not at all important. Well, not at all important is down here. It's E. And if we find E, 136 people said it was not at all important. So put 136 over 989. Put that in your calculator and you get 0.138. Okay, what else we have? So then you have that a story is not too important or not at all important. So that would be D and E. It says or, so we're going to add them together. And these bar charts are all mutually exclusive. So I have 189 plus 136 all over 989. And then finally on the bottom, it's extremely important or very important. That would be A and B. So same thing. The word or tells me to add, and then put it in your calculator. Right, so when we were using the pie chart and the bar chart, they are already mutually exclusive when you have a pie chart or a bar chart. There's no overlap. But when you start getting words, you start picking cards, then you have to watch for overlap. So A is compute the probability of randomly selecting a diamond or a club. Well, a card can't be both. They're either a diamond or they're a club. And so those are mutually exclusive. And we can just add those probabilities together. So the probability of picking a diamond is going to be 13 diamonds out of 52 cards. Remember, this is or, so we're going to add. And then the probability of selecting a club, again, there's 13 clubs out of 52 cards. Put that in your calculator and you're going to get 0.500. Then they say a diamond or a club or a heart. Well, again, those are all mutually exclusive. We have 13 of each. So if you add 13 plus 13 plus 13, put it over 52, you get 0.75. All right, the last one is the one we have to worry about. So this one, we have a 9 or a diamond. So now we have overlap because there is one card that is both a 9 and a diamond. That would be the 9 of diamonds. Okay, so we have 4 9s. Right, there are 4 9s in the deck, so 4 out of 52. We have 13 diamonds. That would be 13 out of 52. But the problem is we have now double counted, right? We've double counted the 9 of hearts. It is in the 4 and the 13. So we need to just take one of those out. And that leaves us with 16 over 52. Put that in your calculator and you get 0.308. So the probability of randomly selecting a 9 or a diamond would be 0.308. Right, this one gets a little trickier. I like to draw a graph. I draw my Venn diagram so I can take a look at what's happening. So a physics class has a total of 50 students, okay? 17 of those students are physics majors, right? 17 are physics majors, 18 are female, and then 6 are both. Okay, so that's where the trick comes in. 6 are both. So if I draw my Venn diagram, I've got physics over here, this circle, and female here. I know that 6 of them are both, right? They're a physics major and a female. So if I look at this, that leaves me with, I had 17 physics majors total. So that would leave me with 11 that are physics majors and not female. And then I had 18 total females. So that would leave me with 12 females that are not physics majors. Okay, so now I have a couple choices. I don't have to draw the Venn diagram. I can just grab the probability. Remember, there's 50 students. So the probability of the student being female would be the 18 females out of 50. The probability that they would be a physics major is 17 out of 50. And then I know that those 6 female physics majors were counted twice, right? They're in the 18 and in the 17. So I would have to subtract out one of those since they were double counted. And that gives me 0.580. The other thing I could do at this point is just because I drew the Venn diagram, I could just add my pieces together from the Venn diagram, and that would actually give me the same answer. Okay, so either way, however your brain works. All right, this is another table. This time we have males, females. We have whether they support a tax to fund education, they oppose it, or if they're unsure. Okay, so our total number of adults is 1,059. The first one says, find the probability that a person opposed the tax or is female. So if you look at your table, the number of people who oppose the tax, 627. The number of females, 555. But the problem is there's an overlap, right? Because we have in the middle here, we have 297 that they both opposed and they were female. So we need to subtract those out. I'm just getting this set up for you. Then you could put it in your calculator and get the percent. The next one is supports the tax, which is 404, is male, which is 504. But again, we have an overlap. We have an overlap of 167 here. They supported and they were male. So we need to subtract that out. Whew. And then finally, we have a person is unsure or is not unsure. Ooh, watch for those nots. Is not unsure. So that would be the 404 who support. That would be 627 who oppose. Then we say or is female. So that would be 555. But now we got to watch because now we have a couple of overlaps. So we grabbed 404, we grabbed 627, and we grabbed 555. And so we actually have two values of overlap. We have females who support and females who oppose. So I have to actually subtract out both of those. It's easier if you just look at that chart one-on-one, but this is just like the blood type problem. You just have to be careful of where you have overlap.